In this video, we're going to be going over the process of path analysis using SPSS. And I wanted to start with a diagram from the Mertler and Reinhardt textbook in Chapter 8, which shows the overall diagram of the model. And we've got several different equations here that we'll test as separate regression models. And you can see here's the legend for what these different variables mean. Number of doctors, the GDP, the death rate, the birth rate, and then we're trying to predict the infant mortality rate. So we've got several different configurations of variables going on. We're going to have to test these individually. So we'll come over to SPSS and we'll take a look at the first equation. We'll come to regression and linear. And the first equation we're looking at is the number of doctors as natural log transformation, predicting the death rate. We've got the transformed version of number of doctors predicting the death rate for the country. Under statistics, we want to have model fit, collinearity diagnostics, and estimates selected, and that will be it for our preparation. We'll click OK, and there are the results. We see an R-square of 0.414, adjusted of 0.409, so this one variable predicts about 40% of the variation in the dependent variable, the death rate. So the number of doctors is pretty important. We come down to the coefficient. We see the standardized coefficient is negative 0.643, so the more doctors there are, the less the death rate is going to be. We'll then move on to our next equation. Analyze, regression, linear. And this time we're going to take a look at the effects of the GDP, the gross domestic product, and its transformed version, the natural log, predicting the birth rate. We'll leave everything else the same and click OK. And here we see there's a rather large R-square, 0.645, adjusted down to 0.642. Significant F statistic. The coefficient shows a very large effect. The higher the GDP, the lower the birth rate. Right? So very high number. And then we'll come to our third equation. Analyze, regression, linear. And this time we're going to be predicting the infant mortality rate with the number of doctors logged, the birth rate, and the death rate. We'll click OK. And there are the results. This time we have an adjusted R-square of 0.876, meaning the model predicts about 88% of the variation in infant mortality rate. We have a significant large F statistic, meaning the analysis is valid. And the coefficients show the effects of each individual variable. We see a very strong effect for birth rate, followed by death rate, and finally number of doctors after that. We see all the variables are significant. However, we also see some indicators of multicollinearity. We have VIFs over 3, and we have tolerance statistics over 0.10, all of them. So that may be a concern. If we return to our diagram, we can see or be reminded of the paths that we were creating. We'll have to do some more work, but essentially here's Z5, that's the infant mortality rate, and that is being specified as a function of Z3, the death rate, Z4, the birth rate, and Z1, the number of doctors, and we logged GDP and doctors. And we have the death rate as being caused by the number of doctors, and we have the birth rate as being a function of GDP. So we've got a few different equations. Each of these represented a regression analysis, and now we have to do a little more work to get to our final path coefficients. In the Mertler and Reinhardt textbook, they do the work for us in this example. So what we're looking at is path decompositions and calculation of reproduced correlations for the model. And the correlation for each equation is listed here, and here we're plugging in the actual values that were generated through the analysis. The 3 regression analyses that we did to inform our path analysis. Here's the next set. And the final calculations. The end result can be presented in a table form, as we see here in Table 10. And here we've got the observed correlations and the reproduced correlations down below. So you can have a nice comparison here. Right? We're decomposing the paths, taking into consideration down here the other variables that were causing the independent variables, the endogenous variables. And if we add the reproduced path coefficients into the initial diagram, this is what we see. And now this is a little easier to interpret. So we can see that infant mortality is strongly caused by the death rate, the birth rate, right? That's Z4. But also the death rate, not quite as strong of an effect, and also the number of doctors. But we can also simultaneously examine causes of the birth rate as the GDP, which is a major cause, as we can see with that large coefficient, and the causes of Z3, the death rate, which is the number of doctors, right? Also a very large negative correlation. And you'll notice all these are significant. And this last one is the simple covariance of the exogenous factors in this path analysis, which are the number of doctors and the GDP. And those also, as you note, correlate very highly. And as Mertler and Reinhardt show through additional analyses that test the invisible or missing paths, which essentially means examining all the possible pathways between variables, that they found it was important to include this path, where the number of doctors also predicts the birth rate, not only the death rate as in Model 1, and again a negative and moderately strong correlation pathway there, the coefficient, and they removed another pathway from was it GDP? Yeah. So this is the new model after the revisions. And the Model 2 analysis can be presented as a table that shows both the direct, the indirect, and the total effects. And this helps us understand some of the causal pathways involved with predicting infant mortality.